So yeah, I'm trying to improve things. All right, here we go. I'm the fake person video now, okay? All right, so any case, let's go over some things. Now, we weren't together physically when I did this, but I had a nice video I think that really, really worked, and I want to work you through this. Okay, now, if you notice, the video that I did make wasn't this class, because I thought I was better the second time around. I think I put it together better in that 40-minute thing. Any case, so let's continue and reconnect. The whole purpose of the second law of thermodynamics is the delta S of the universe must increase. You have to understand that a favorable, okay, condition, it's more than just favorable. What defines whether a process will occur is a spontaneous one, is an allowable pathway. A thermodynamic pathway for something to go. There are pathways and there are no pathways. As we talked about, the first law of thermodynamics is an uplifting law. Hey, delta E of the system equals negative delta E of the surroundings. Anything's possible because delta E is made up of what? Any level of what? Remember delta E is equal to the Q plus the work, and you can have any amounts of work in Q, possibly. Hey, we can have an engine that's what? 100% efficient, that gives off no heat, and all the energy changes the work. Anything's possible. Maybe the energy released from our internal combustion engine, our car, can be converted back to the system again perfectly. And we can just have renewable energy. No! Second law of thermodynamics says, hey, this is true, that energy is convertible, and we don't lose any. But, oh, it's a bummer, the second law, because it states that the delta S of the universe must increase, which means that not all of this is possible. Every pathway of delta E is not possible. So this is an uplifting law. Anything's possible. This one says, no, everything is not possible. Yes, delta E of the system is negative E of the surroundings, but how you get there is limited by the delta S of the universe increasing. If the delta S of the universe does not increase, there is no thermodynamic pathway for that to get there unless you add energy to the system. And I say you have to not ride the pony, you got to carry the pony. If you've got to put energy in to force something to work, that is going against the thermodynamic pathway. Best example, photosynthesis. Light has to be on. You need to have light to create photosynthesis. Turn off the light, no photosynthesis. What drives photosynthesis is that you have to add what we call free energy into the system continuously. So this is a bummer. And then you have the third law that says that the absolute entropies, that's the measured entropies, okay, equals 0 at 0 Kelvin, okay, which is a kind of a weird law because this says, hey, anything's possible. No, it's not. We're limited by the entropies starting from 0, yet we can't quite get there because of second law. Kind of weird, okay? So that's where that comes from. Now, if you don't quite get there, this absolute entropies we talked about introduce a new way to think about measuring a thermodynamic quantity. Forever I've been talking about the fast, starting high and going low. But I can't do a straight line up here. But now I've got the what? Got the as, don't be as. Okay? So I've got a what? Absolute zero zone. We measure entropy from 0 what? Kelvin. And then we use constant temperature systems. Hey, this might be the what? The increase of entropy as a solid and a crystal state from 0 of every compound, excluding a few. Okay, hydrogen doesn't like to be a solid, all right? But in any case, 0 Kelvin going up gives me what? This could be the melting point. Melting, hey, doesn't that occur at a constant temperature? Constant temperature, okay? So we measure the energy changes, okay? And then we finally get to the 298 Kelvin. That's the standard, okay? That's the 25 degrees Celsius because the scientists who were measuring this didn't want to work in a freezer at 0 degrees Celsius, 273. So this is the what? The as zone. So we're measuring what? The absolute entropies of molecules, which is listed for you in your tables. And if this is the reactants, and this is the what? Products, what just happened? My delta, my S of the what? My absolute entropies of my reactants are now lower as products. What's that? Is that a favorable thing or an unfavorable? If my delta S of my system went down. Is negative. Is that a good? Absolutely not. What did we say, the second law? This must do what? Be greater than 0 working this way. Okay, so delta S of the universe must be greater than 0. Now, hold on to your ponies for a second. When we're measuring chemicals entropy changes, first and foremost, how do we do this? In your reference table, delta S of your reaction is equal to the sum of what? Delta S of the absolute entropies of the products, what? Minus the sum of what? The absolute entropies of the reactants. Why? If I want to get a positive value here, don't I need a what? Smaller number minus a bigger number? That's why it's products minus reactants, unlike what? Bond energies. Okay, forget all this. This is the basics. Now let's continue. All right, here we go, party people. Now, if this is true, all I want is an equation that will measure the entire what? Universe. Now, party people, we can measure this. This we get from tablature. Right? And that is what? The sum of the absolute entropies from the tables of the products minus the reactants that will give me plus or minus. But this, party people, is only for the what? Molecules or particles in system. This is what I call the molecular freedom. But only in the system. Don't get lost in the sauce here. We have a system. And what else do we have? We have a what? Surrounding. And that surrounding the system is the universe. So when I'm looking for the delta S of the universe to find, hey, does the delta S of the universe increase in this process? That would mean a spontaneous process. There's a thermodynamic possibility, okay, if the conditions are right. If it's not positive, not increasing for both the system and surroundings, then there's not a what? Thermodynamic pathway under those set of conditions, and we would say it's non-spontaneous. That's important. You've got to grab this. But all we got right now is looking at our system. But darn it, we need the entire what? So how in the world do we get the surroundings? Well, if we do constant pressure, what do we know about constant pressure? Okay, with constant pressure, if Q is equal to negative, what does that mean for this system? The Q is what? Positive for the surroundings, correct? I should do it up there, right? So the Q is what? Positive for the surroundings, correct? And if I'm in constant pressure, doesn't the Q of the surroundings equal the delta H, negative delta H of the system? Yes? Don't we know at constant pressure calorimetry? NASA grade calorimeter? Looks like a regular cup, but they kind of like it look that way because people would steal this and put this on eBay. Okay, now they gave it out. People are running to do that. Okay, but yeah, so negative. So what do we just do here? Well, what do we know? This is important. This is the biggest leap. If heat is released into the atmosphere, aren't these molecules going to expand more and go faster? And aren't they going to disperse? Hey, we can relate the what? We can relate the dispersion of energy with energy flowing out of the system by using what? The delta S of the system. Now what I did is in the derivation, okay, we did what with that? Well, delta F of the system divided by what? Constant temperature. What does that give me? That gives you, party people, delta S of the surroundings. That's how we solved. Hey, if the Q was positive for the system, what does that mean? Energy rushes in, correct? And if energy rushes in, the surrounding gas molecules are going to go slower. Are they going to disperse? No. Higher temperature means that they move more and move away. That's increasing the entropy. What is entropy? the movement from concentrated source to less concentrated source. And particles is what it's about. Particles moving outward because you release energy is going to do what? Increase the energy of the surroundings. So what do we learn? Okay, so we did all of this, and I'm not going to redo this, but bottom line is, we found that the Q delta S, delta H of the system, okay, plus the delta S, this is delta H of the system, delta S of this system is the tablature, okay, and this is negative Q over T. What do? We times by T. In fact, we times by negative T, okay, because it's in this delta S of the this is what? The universe. We learned what? S is equal to the Q at constant temperature over temperature. That's what this is. We found that this, delta S, is surrounding. We found that this was from tablature. So now all we're going to do, party people, is divide times by negative T. I guess I am deriving it. Can't help myself. So I times by negative T. This should be Q over T, sorry. This gives me what? Negative Q is equal to what? Negative T. All right, so this becomes positive, I'll write it there, delta H of the system, right? Negative T over, and this becomes what? Negative T delta S of the system. Now, negative Q is delta H, but more importantly, the energy. We're going to measure Q, joules, kilojoules. This, my friends, is what we call Gibbs free energy, delta G. And when we measure Gibbs free energy, we're measuring the joules of free energy that's available. Hey, does the universe increase or decrease, or increase or decrease overall when you look at the systems, okay, how the particles are changing with tablature, and the surroundings by the heat exchange? That's important. This is the heat exchange. With constant temperature, constant pressure, we can look at the systems, delta H, and the system's particle change to reflect the entire universe. That's the power in this formula. So delta G is delta H of the system minus T delta S of the system. The most important fundamental formula. Okay? We can look at system qualities and relate it to the universe if temperature and pressure is constant. That is the most powerful. And what does this measure? Energy. But specifically, it measures free energy. And free energy is the energy that you can make something happen. If something is spontaneous, this delta S of both quantities, or at least overall, I should say, increases, which means you are spontaneous, which means you're going to get a negative delta G. And if you've got a negative delta G, hello, delta G here, here's time, you're starting high, going low. That's a change in delta G. Delta G is negative because you're starting with something with free energy. And what are you going to do? You're going to use it to boil water, turn a turbine, make electricity. You're going to use it to move your car. Things that have high stored free energy, you can use to do work. You're riding a pony, okay, and your ride takes you where you want to go. But if you go opposite, like photosynthesis, and you're going against the thermodynamic pathway, to go up in energy, we're going from what? Glucose. I'm going from O2 and water. Okay, I'm sorry. We're going to go from CO2 and water. We're climbing this. Delta G is what? Positive, which means what? You need free energy to make that happen. Now I'm carrying the pony. Now I'm forcing the process. When I lit the paper in class, I didn't have to keep adding. I didn't have to keep the what? The lighter on. And as soon as I pulled it off, it stopped. It was self-sustainable. Okay, so how do I relate that to the signs? This is so important. That's why I'm doing it again. So let's go let's get rid of this, and let's go talk about that equation now. I'm going to keep this up. Don't lose sight what this means. So here's our equation. We're going to relate delta S of the units with delta G. delta G is equal to, hey, we relate the delta S of the surroundings by what? Delta H of the system. And then we're going to relate what? The system minus T delta S of the system. Little s in here, system. That, by far, is the most important thermodynamic quantity we can have. Okay. Now, real quick, what do we know? Well, it's got something called the always rule. Why is it always? Because it's always going to give me a negative value. Hey, delta G is negative. What does that mean? I'm starting with something with high delta G, low. Why? You're going to use it. We do spontaneous process because what? Free energy is being used. We take glucose in cell respiration. We break that high energy bonds. We make ATP. That ATP's got what? Free energy that we use to drive things that are non-spontaneous. Remember coupling? Okay. Now, what always gives me a negative? Hey, think of my system. First off, heat being what? Given off. What's that do to the surroundings? If heat is released, if the reaction is exothermic, what does it do to the surroundings? Increases its entropy, correct? The molecules of gas on the outside are going to move faster. If they move faster, they expand. You're dispersing heat. Heat is going from a small area and dispersing out. Hey, the surroundings. That's what this is, party people. Okay, increases if delta H is negative. Why negative? Because if you've got some enthalpy and you've got heats of formation going down, there's an overall delta H going down because energy was released. Okay, so what is this value? Negative. Okay? Now, what about the system? This is important. Exothermic heat's released. Now the system, if you've got something where, hey, I've got a solid breaking apart into what? Free ions that are aqueous, isn't that going to do what? One particle breaking apart into two? Aren't I dispersing the particles? Aren't there more degrees of freedom with two ions moving than just one? I know this is not a particle. Okay, so this would be positive. If the entropy of the system's increasing, what does that mean? The particles are going from a what? Solid to a liquid to a gas. There's more freedom as you go that way. Or hey, you get 7 moles of molecules, then you make 10. Hey, entropy increases. Okay? Now, let's do the signs real fast. Plus a what? Negative. What's a minus plus a negative? Always. Negative. Think about it. My system's entropy increases and my surroundings increases. Isn't that going to give me always an increase in total entropy of the universe? Yes. Where's the never rule? What's the sign for this? Positive. How do we get there? That means we need additional free energy to make this happen. That's carrying the pony up the hill. It's photosynthesis. So this must mean to always be positive, we have an endothermic. Delta H is positive endo. You got to get that down. You're absorbing energy. Minus, hey, this system's entropy is going from a gas to a solid. 8 molecules to 4. Okay? So this is going to be a decrease in the system. This is energy going what? Sorry, I should leave that box here. Heat is going in. That means what? Energy from the surroundings are going into a concentrated little area, and these molecules are now going slower. Okay? So that must mean that the delta H is positive. Don't forget, I know it represents this. Remember? Don't get lost in the sauce. Delta S of the surroundings is what? Equal to negative delta H of the system over T, right? So if this is positive, okay, you can understand what that means. But any case, what is do the math? What do you always get? Always get a positive. Positive delta G means you need free energy to make it happen. It's not free anymore. You got to use some to force it to happen. Always non-spontaneous. And here's where people messed up a lot last night. Okay? The sometimes rule. And it pops up a lot. Okay, let's do the first one. Okay? All right. Let's do delta H is negative. Now, is that exo or endo? Is heat going into the system or out if the delta H is negative, which equals negative Q of the system, right? Energy is going out. This is exothermic. Party people, this is a favorable. Why? By increasing delta, by having a negative delta H, you're releasing heat. What does this do to the delta S of the surroundings? By releasing heat, does it go up or go down? It goes up. Correct? That's good. That means that this could increase, but I got to check this out. Okay, now, it's a sometimes rule. Minus T delta S. Well, let's make it go what? Let's make it be negative, bad, unfavorable. Now, a great example of something exothermic, okay, that is going against the universe, this would mean what? My delta S is decreasing. And that's why it's sometimes. Okay, now do the math. Plus a what? Right. So when can this be negative? When this is big enough, correct? Only when this is big enough. Now think of an example of something exothermic, okay? Let's look at a heating and cooling curve.
Don't you mean when it's small enough to be or the negative's big enough?
Well, right now this is a positive expression when I go plus plus.
Yeah, so shouldn't the negative be the bigger?
I'm sorry, yeah, my bad. Yes, yes. So I want to make this negative, thank you. I want to make this negative, so I want a small enough temperature that'll make this positive small enough. Thank you for stopping me, okay? That'll make this have a possibility to be sometimes negative. So when do we have a small enough temperature? When do we see things happen when the temperature is lowered? Freezing! What is freezing? H2O liquid. Go into H2O what? Does water always freeze? Does water always freeze? Only at low temperature. So water mostly is on spontaneous freezing until you reach a low temperature. If the temperature drops, it makes this expression bad. Now stop for a second. How come a liquid to a solid is exothermic? Well, this is a gas. It's a liquid. Remember, this is gas, liquid, okay? Solid, this is the phase change right here, right? Aren't we going down? Don't liquids have more energy than solids? So to go from high to low, don't I have to release energy? Oh, wait a minute. I'm going from something with more freedom to a crystallized structure. My what? Delta S of the system is doing what? Decreasing. I know I made it a positive there. We did the math. Okay, good job. So that's only in that case. Now how about this one? Let's make something endothermic. Okay? That means what? When delta H is positive, heat is going in the system or being released? It's released or absorbed by the system. It's absorbed, which means it's taking energy, consuming it, making the surrounding temperature go up or down. Correct. Temperature drops if the system grabs energy, like an ice cube. Okay. Minus T delta what? Now let's do the opposite. Okay, this is unfavorable. This is not good, right? So that's going to do what to this? Okay, good. This better be what? Big enough to make that happen. So I'm going to make this favor. Now this, if this was what? Negative, all bets are off, not going to work, but this has to be what? Positive. So party people, okay, what we have here is an increase. And guess what? For this to work, I better have a big enough delta S of the system to overcome the energy loss by the surroundings that made it go slower. Okay? So do the math. Plus a negative. Oh, sometimes again, right? So what was this? This was a plus a negative. This was originally what? This was a positive. Yeah, let me not get rid of it. My bad. Okay, so plus a negative, so it's going to be negative sometimes. When what? temperature is high enough. Does water boil at every temperature? Is it spontaneous? Depends. Well, yes. But if temperature is constant, constant temperature, constant pressure, these things, okay? Water goes from what? H2O what? Liquid to H2O what? H2O gas. Hey, liquid to gas. Is my what? System's particle freedoms increasing? Yes. It better increase enough. Now, however, to go from a liquid to a gas, remember your what? Heating curves? Don't I need energy to climb that ladder? Don't gases have more energy? You require energy. That's unfavorable. Okay? So the only reason, what are we going to do here? We need a high enough temperature change to make this expression big enough to overcome this bad. Now, let's review. This example here that I just showed you, where the entropy was positive and with the temperature, is called an entropy-driven. You better get that down. Entropy-driven. The entropy was what? Great enough to overcome the unfavorable loss of energy, or loss of energy from the surroundings, or in this case, loss of what? Delta S. Hey, in this case, weren't we originally negative here? That's a bad. So in this case right here, what do we have for arrows? We have a delta S of the system that's dropping. The molecular degrees of freedom are dropping. Hey, but this was what? And it better be big enough. So what kind of tribute? So who's the fave here? Okay? And this better be a more negative enough to overcome this N. So this is it entropy? No, it's enthalpy. Enthalpy driven. I did all this in the signs. I don't think everybody watched it, okay? I bet you people watch it double and 3 times. Okay, quickly, let's go through this. Okay, always a spontaneous reaction. What do you think? Always, the change in enthalpy with what? Delta, no, let's do this. If it's always spontaneous, isn't that the always rule? What's a change in free energy? If I'm going to be spontaneous. Negative. Why? Don't forget why. Because you're releasing it so that you can use it. Spontaneous process of negative delta G. Write it in that packet. Okay. It's always, which means a change in the entropy. I should say system, right? But hey, I'm tall. Must be positive. That means the particles have more degree of freedom. Change of enthalpy? Negative. What's that mean? Energy is being released to make the surroundings. This is the system. Particles are getting more freedom. 2 moles becoming 8 moles. Solids becoming gas. That's the system. This is the what? Energy change that we link to the surroundings. Okay, next. Never spontaneous. We have 2 unfavorable conditions. These are 2 faves, 2 unfaves. Therefore, energy must be, let's go to the delta G first. Must be what? Positive. What else? That means the change in entropy should be what? Negative. That means that of the system, this is going down, and this must be what? Going down. So therefore, the delta H must be what? Positive. Energy is what? Flowing out. You've got to have this down. Spontaneous process. That is entropy driven. Hey, if it's entropy driven, that means that the what? Okay, first of all, it's a spontaneous process, so delta G is what? Correct. What else? What else? Okay. Now, if it's entropy driven, that means that we're going to have a favorable condition for the entropy, right? And then we're going to have an unfavorable for the enthalpy. Bad Brodsky, no. There you go. This is bad. Delta H is flowing out of the what? Surroundings. Into the system. You're getting slower. This is decreasing. But this better be great enough to overcome. Good. Process enthalpy driven. Is it entropy? No, it's enthalpy. Delta H. So, what's a favored condition? Negative delta H. If it's spontaneous, what's the delta change of free energy? And that means it's the sometimes rule. This is good, but what's bad here? Delta change of the entropy of the system must be negative there. Okay, now I'm going to apply it to something that we've seen. How dare I apply it to something? What is sublimation? Sublimation, here we go. CO2, solid, going to directly to a gas, CO2 gas. We saw this up close and personable. First and foremost, do you think this requires energy or does this release energy? When you guys were handling, was it cold? Therefore, it was doing what? Making the surroundings cold. So therefore, we would put the energy right here. The energy goes where? In the reactant side. If it was exothermic, we would put it here. So energy plus this made the gas, correct? So this, party people, had a change of enthalpy to be positive, an unfavorable condition. Dry ice was taking energy from your hands, the table. It had to. It was going from a solid to a gas. Bad. It made the environment colder. Anytime the environment's colder, you have a delta H. That's positive. You dropped sodium chloride in water last week. It made the water colder. The dissolution of the salt was endothermic. Correct? Now, party people, it did happen, didn't it? Did dry ice in front of you become solid, become gas? Yeah. So we know it's spontaneous. Boom. It wasn't driven. It did it by itself. You pushed it around. Now, this was bad. This is unfavorable. This happened. What must have overcome the bad? Right, and hello, solid to a gas. Isn't that a tremendous leap in particle movement? So the delta S must be what? Positive. Okay? Now, hold on to your ponies for a second. Now, this will let you know, just so you know where you stood. The first row was 81% of the group. This was 77 or 78% got right. The third row of the entire students who did this, only 52% got this right. This row, 52% got right. And this is 44. Okay? So hopefully that helps a little bit. Now, I'm going to give you a break in a second. We're going to go on to number 5. Okay, number 5. I will give you the break. Now, in number 5, okay, only 52% of the students got this right. I was showing you a video I thought would take off. I haven't really. I made the balloons up different percentages and slow-mo. I thought it was like one of my best videos, and I got like two views. I'm forcing you to look at it to up the views. Okay, no. So what's this reaction? What's the reaction? We're taking hydrogen in the balloon plus what? Oxygen, and we're making water. By the way, okay, hydrogen. Gen in Greek means maker. Hydro maker, water maker. Okay, so this is the reaction. Okay, first of all, did it give off heat? So where is the heat in this reaction? On the product side. Right there. It's exothermic. It was producing those products and heat that was released. So what do we have here? I got a favorable condition. That means that this is going what? Up, correct? Now, what's bad about it? 3 particles becoming what? Just by itself, that's bad. But then we have what? 3 gases becoming 2 gases. So we're doing what? Lowering the moles of products. What's happening to the degrees of freedom? We have 3 individual particles now becoming 2. So the delta S of the system is decreasing. That is unfavorable. That is what? Negative. I'm not sure which one was negative. Yes, there we go. There we go. We've got this law right here. Okay, except we're not going to involve temperature. In this case, it was a chemical reaction. Did it work? Pretty violent, wasn't it? Pretty spontaneous. Hydrogen spontaneously works. Now, rate of reaction is not linked to spontaneity, so don't fool with that. We'll talk about that later. But this is a very spontaneous reaction with the what? Activation energy. Why? What we got here? Plus Plus, right? So why did this work? Bad entropy of the system, but what was good? This gave off so much what? Heat. That the surrounding molecules, could you see how much the surrounding molecules got by the reaction? This gave off so much heat it overcame this. And this is an example of an enthalpy-driven reaction. Okay? So that's why you get what? You got heat was released, negative. Delta S, negative because you're going from 3 particles to 2. 3 moles to 2. That had to be negative. I know your signs. And then delta G, did it work? But negative. That's why that was there. Too many people got that wrong. Number 7. All negatives. Number 7. This was a relation to bond energies. Okay. Bond energies. Okay, I'm losing space here. But, okay, last little piece. I'm going to get rid of this. Oh, beautiful. Okay, look at the reaction here. What does this mean? CO2 gas. Gas! Plus what? 2H2. Gas! Now, I don't like this equilibrium stuff, but let's just go one way. Becomes CH3, OH. Hey, delta H is less than 0. What does that mean? It's exothermic. Where does the heat go? Reactant side or product side? You're producing it. Heat, joules, sometimes you put that there. Okay, so let's draw an energy diagram. Here's my what? My phase. Okay, bottom line is, this is my potential energy, right? Pot energy. Okay, we'll get into frying pan energy next period. Okay, now, phase. Really? Okay, if heat's being released, are we going from a high? And who's high? CO2 plus 2H2. What does this mean? The collective heats of formation of these guys from their elements gives me that. If heat's released, aren't my products here? The collective, oh, it's only in this case, heat of formation, okay, is here. Okay, but bond energy, what's that mean? Hey, it's the opposite way. This is the energy needed to what? Break these bonds. This is the bond energy of the what? Products. When you do bond energies, isn't this exothermic? Yes, you're going down. Delta H is negative, yeah? Good. So we need a negative value. If I'm a robot and do products minus reactants, that won't work. So what we do is, and you need to know this, the bonds broken minus the what? Bonds formed. So what I really do is, hey, the bond energy to break this is the same energy what? Released when I form them. So if it's exothermic, and you know it is because they told you that, and this means delta H is negative going down, delta H of the reaction must be negative. So what? It must be that the energy to break these bonds is smaller than the energy released to form new ones. Every single chemical reaction, in order to what? Rearrange, to have new things. Chemical reactions are a rearrangement of the particles. You have to break the bonds first to make them into what? Free atoms. Then the free atoms do what? Form new bonds. So what do? Very simply, if it's exothermic, the energy absorbed as the bonds and the reactants are broken is less than what? Than the energy released. Okay, and that's the best answer. 50% got that wrong. Okay? All right, take a break, please. I'm going to give you about 5 minutes.
You said please, so I guess I should have. Yeah.
Oh, sorry, CO should be there. All right, so I did this quickly at the end of the class, but I want to make sure we're on the same page. Okay? So what I have is I have these sodium acetate, okay, packets. work?
Oh, is that not what you meant?
Okay, so I have these sodium acetate packets. Okay, so you can see, let's just put them up here.
I'll put it, yeah, I'll put it later.
Okay, and we're going to autofocus this baby. Okay, now you see the little metal discs in here? These little metal discs, if I crinkle them, they make a noise. They make compression waves. Now what I have is supersaturated solution here. This solution has a lot of what? Na plus and acid. This is the acetate ion. They're actually hanging out as ions, positive and negative, in high concentration. But they're so disorganized, they're not in a crystal pattern. So these are just kind of disorganized ions. Remember, to be in a crystal pattern, you have to have a repeating regular geometric arrangement. So when I dissolved this, I dissolved a lot of sodium acetate. I added energy, free energy, to make them dissolve. Then I cooled them slowly. Because this acetate ion is so big, it's hard for it to get into a crystal arrangement by itself. Now, this is unstable. This has high free energy. Now, why? Because I dissolved it. Now, by crinkling the little disc, I actually make some sound waves. What's a sound wave? When a sound wave is propagated, aren't I going to push molecules closer together? It's called a compression. And when they push them together, won't they push off to make other molecules together? And you're going to have what we call a compression wave. And this is how we propagate a wave by sound. Remember that? Remember the Rubens tube? So if you push these guys together, what are the chances they're going to find a crystalline pattern? Pretty good, randomly. By pushing them together, just by chance, they'll start a crystalline pattern. Once you start a crystal pattern, they can start adding to the rest of the pattern. Okay, so we're going to watch what? Solidification occur. All right? So solidification is going to occur. So here I go. I'm going to make a little sound. Get back here, little disky. Can you still see me?
Yes.
Okay, get back here.
No, not anymore.
Am I good?
No.
Good.
Yeah.
All right.
Crinkle.
Miss
And then you can see it becoming a solid. Now, look at the reaction. In terms of the systems, entropy, particles, is this favorable or unfavorable? Two particles becoming one. Aqueous free becoming a crystal. So this is what? What's the charge? Negative. But wait a minute. You just saw this occur. So what's the charge? If this occurred, wasn't it spontaneous? The only way for this to be what? Unfavorable. This better be what? So that must mean that energy must have been absorbed or released. Is that going to work? Can I have two unfavorable? You guys are not paying attention. You're saying yes because you must be right. Do the math. Right. Why did I write positive? Watch. If this is negative. Because I'm watching. Why don't you say no?
I just.
What's going to happen? This is never going to work. Did it work? It worked in front of you, so this can't work, right? So this is negative. So I need a favorable condition. So energy must be what? What would we call this? Entropy driven or enthalpy driven? Right. So party people, this better, any kind of solidification must be what? Must be what? Come on, do some. Do some. Crinkle them. Crinkle them. Crinkle them. Crinkle them. Are they warm or are they hot? Are they giving off heat?
Yes.
They better. If you're going to go against the grain here, party people, if this is going to be unfavorable, you have to, if it's going to occur. If solidification occurs, this has to be exothermic. It has to overcome this unfavorable condition. Because what? Negative minus a negative becomes what? Plus what? Plus. And party people, This expression must be great enough to overcome this bad, which means this is what? Enthalpy driven. So I said in the video, if you had plaster of Paris, clay molding, cement solidifying, nail polish solidifying, anything that solidifies must be exothermic. If you ever had a cast being set on your arm or leg, it feels warm at best, because if it didn't, it wouldn't work. The only way allowable for something to become a solid is it better give off heat. Not sure if I did that great, but hey.
Is your delta positive? And your, no, is your delta